have instructions stored in the data memory, you can execute them. You can play with the program counter and tell it go to the data memory. Okay, on the other hand, hardware architecture devices, okay, program and data memory spaces are physically separated. Okay, so in hardware architecture devices, you cannot send messages containing instructions as their payload and actually execute them. So Goodspeed, what he did, he managed to send one message, okay, containing 2 or 3 instructions, okay, depending on the message size, but usually the message size in sensor network is small. Imagine the default packet, which is usually most of the application, is 24 bytes. Okay, so you can actually send 4 or 5 commands and execute the commands that were sent throughout this message. Then these 2 guys that come from France, okay, I will not try to say their names, then demonstrated the code injection of devices with the hardware architecture. But because of the nature of this kind of architecture, it has a lot of limitations. Okay, first of all, as we said, you cannot execute new code instructions that can be sent through a message. So what they demonstrated is actually how to execute a sequence of instructions that are already stored inside the program memory of the node. Okay, they call these things gadgets. Okay, so first what they do is they find the memory map of the node and they find instruction sequence that they can use, like sending. Okay, so they create some gadgets and they show that if you can use a chain of, you can execute a chain of these gadgets, okay, you can actually inject a fake stack inside the node, okay, byte by byte, and then actually inject a new program image. But the big thing here is that since you inject a fake stack, which is really big, it's like 256 bytes, byte by byte, you can imagine how much time this takes. Okay, so obviously, such an attack can be detected by the administrator. Okay, and it's not that, okay, you have to find, okay, specific instruction sequences inside the memory map. Okay, if you cannot find the instruction sequences you want, so if there is a guy that knows what the instructions are used in order to inject fake stacks, so you are not going to be able to do such any code injection attack in hardware architecture devices. Okay, so that's why we target also the von Neumann architectures. Okay, that's why you use TMOS high sensor devices. As you remember, they have the MSP430 microcontroller, okay, which is based on von Neumann architecture. So what we did is we took one step further the work of Travis Goodspeed and actually managed to inject and execute arbitrarily long code, not code instructions that can be sent only through one message. Okay, and then we use the radio capabilities of each one of the sensor nodes and actually create a self-replicating worm, okay, that propagates the carried malware throughout the whole network. So what we achieved is by infecting only one node, okay, which takes 30 seconds. Okay, eventually you can compromise after 2 or 3 minutes, because we have done some tests, you can compromise the entire network. Now let's talk a little more about this. So as we said, we target devices following the von Neumann architectures. Okay, the instructions and data are stored in the same memory space. Okay, here you can see the memory map of the MSP430 microcontroller. Okay, we use the JTAG in order to find these things. Now the hint behind being able to inject arbitrarily long code inside the network is that sensor nodes do not support dynamic memory allocation. Okay, so all memory that is needed for data storage variables function, okay, is found and allocated during compilation. Okay, but on the other hand, since this is a typical embedded system, okay, they have reserved memory space for the heap. Okay, heap is for the dynamic memory allocation. So heap is over here, and it grows upwards. Okay, so this heap memory space actually remain unused in the sensor networks throughout the whole lifetime of the network. Okay, and not only that, the other thing is that even if you take the node, you inject the code, and you have, let's say, copied to this memory space. Even if you reset the node, the code over there will not be erased. Okay, they have to specifically say to the node, flush all your memory. Otherwise, the injection code will always be there. So what we did, we found the memory that the heap starts. Okay, it's 2574, okay, which grows upwards. And then we used this memory space in order to copy our malicious code. Okay, so you can understand that we can copy a really big piece of code. But always keep in mind that you don't have to, you must not override the stack, okay, which grows downwards, okay, and start from this address, because otherwise the sensor node, okay, will not do anything. It will go to an unknown state and remain there for the rest of its life because it will burn itself. Okay. So the other important thing is that how to map an incoming packet. So actually, again, since we don't have dynamic memory allocation in sensor nodes, all memory addresses that are reserved for specific functions, okay, are the same. So actually, the memory address which is used by the sensor node for storing a received packet remains the same for a specific program image, okay, independent of where you are going to run it. Okay, the memory address it remains the same. So by using a JTAG, you can find this address of where the data inside the payload of a packet are stored. Okay. And again, you can play with it. You can actually do a buffer overflow, override the return address of a vulnerable function, pointing to that address, okay, and then actually execute your malicious code. The most important thing here is this restoration of control flow. Okay. So what this means is actually, if you want to inject a big piece of code, you actually have to send a series of malicious packets, okay, containing your code. So when you send one, let's say the first message, you override the return address of the vulnerable function, you point to the address of where the data of the message is stored, so you execute the malicious code inside the message. After this, you have to be careful to restore the control flow, to restore the sensor node back to its normal state, because otherwise you cannot send any other message. Okay, so actually, you will see that inside every message, we must have a branch command, okay, for making the program counter to point back to the instructions. Now, this is just an overview again. The required steps is first of all, okay, to understand the memory map of the sensor device that we are going to target. Okay, so these are the two things that we said. You must find the storage address of the malware, so actually the address that the heap starts, and you have to find the memory address of the reception interrupt handler. Okay, then you have a transmission of a series of mal packets containing the code that is to be copied into the heap. Okay, so what you actually do is a multi-stage buffer overflow. So each one of the packets performs a buffer overflow attack. And then send the specially crafted packet, okay, for changing the program counter to the address of your code, okay, to the address of the heap actually. Now, this is how it works. Okay, I will go through it fast because I'm running out of time. So actually, the first step, which is over here, okay, so the first step is when you receive, the node receives a message, the variable function, here we have the strcpy, okay, is called. Okay, so what this does is take the payload of the message and tries to copy it inside the buffer. So we have a buffer overflow that is occurring whenever this reception handler is called. So the second step is over here, is since we have the buffer overflow, the return address of the strcpy function, okay, is overwritten by the address you want it. Okay, so you put the address of the, I see you can see it over here, you put the address of where your malicious code inside the packet is stored, okay, and you know this address. So this is the third step. You execute all the code, but now keep in mind that since you want to copy your code inside the heap, okay, the payload of all these messages will contain move commands, okay, because you want to move your code into the heap. So this is an example of such a payload. We have three parts. The first part contains the address of these things over here, of the malicious code instructions inside the packet. So this is used for overriding the return address of the strcpy. This is the second part, which actually contains move instructions, okay. With the default packet size of sensor network, you can send 3 move commands. Okay. And this is the final instruction for restoring the control flow. Okay. So actually, it's a branch command. Okay. So you are copying your code inside the heap memory, and the final step is actually sending a message with a branch command for setting the program counter pointing to this address over here, okay, for starting executing the code. Now, once the program counter is over here, okay, it executes your code. Okay. Usually you put some jump inside, so in order to execute it more than one time, so it cannot go back to its normal state. Okay. It's impossible. The moment that it starts executing your code, okay, it cannot receive any other messages. Okay.